Hi there. Here's my solution to the second AP practice free response question over correlation and regression. So we have some individuals that are looking at data involving the number of commercial aircraft flying in the United States. So their data run from 1990 to 1998. So to simplify their model, 1990 has been recorded as year zero. So right here we have zero, which represents 1990. This is 1991. Here's the observation for 1992. 93 would be here, 94, etc. And this horizontal axis is labeled years since 1990. So something to think about though, this is the residual plot. Here we have some regression output. And here we go. So A, is a line an appropriate model to use for these data? What information tells you this? And the answer is yes, because the residual plot indicates no pattern in the errors of the linear regression model. So this is the residual plot. Remember, in a residual plot, it is showing us the residuals. It is showing us the difference between the actual and the predicted values from the model. And if the model is a good fit, we are hoping that we have errors that are random. If we see errors that actually follow a pattern, then our model isn't a good fit because the model isn't accounting for that pattern. Here we don't see a pattern. In fact, most of the residuals are relatively small if you consider the fact that the numbers of aircraft are well into the thousands. So this model looks like a good fit. I don't have the original scatter plot to look at, so I can't use that to decide if it follows a linear pattern. I also don't have from the output down here, I don't have the value of r squared, so I can't really use that either to indicate whether or not the linear model is a good fit, but the residual plot tells me quite a bit. So part B, what is the value of the slope of the regression line? Interpret this slope in the context of the situation. So you can ignore p, t ratio, standard deviation. Those values are not important for specifying the linear regression model. The coefficients are what matter here, and years past 1990, that is the explanatory variable. So here is the slope 233.5. So I have identified that, and now we need to interpret that. That is the change in the response variable compared to a 1 unit change in the explanatory variable. So a 1 unit change in the explanatory variable would mean a 1 year increase. So for every year past 1990, that would be a 1 year increase. The predicted number of commercial aircraft rises, and again, I'm saying rises because this is a positive slope, by approximately 233.5 aircraft. It's important that you include in your slope interpretation the fact that you are looking at a prediction, you are looking at an estimated change in the response variable. So in part C, what is the value of the intercept? Interpreted in the context of this situation. So under the coefficients, the constant is the intercept. So the intercept is 2,939.93. Again, you could round it to 2,940 if you wanted to. I just left it as a decimal. So the intercept is where the regression line crosses the y-axis, and on the y-axis the value of x is 0. So it's important that you interpret what x equaling 0 means in this context. So this suggests when x is 0, so that means in 1990, that's what x equaling 0 means. In 1990, the number of commercial aircraft flying is predicted to be, or it's estimated to be, approximately 2,939.9. Call it 2,940. Round it however you like. It is more important that you interpret the intercept correctly in context. In particular, every time you see that word context, you need to be writing in terms of what the explanatory and the response variables actually mean. In part D, you're making a prediction for the number of commercial aircraft in 1992. So our regression line has the intercept plus the slope times the value of x. Be careful, the value of x is not 1992, it is strictly the 2. Remember, on the x-axis, right here, these values represent the years since 1990. So you have to make sure when you make that prediction, you put in a 2, not a 1992. So the predicted number of commercial aircraft flying is approximately 3,407. There is our prediction. It is important when you make a prediction to actually show the work. This is very simple to show how you substituted the two into the expression, but showing work even when the work is that simple is important. That is the way to earn partial credit. Then for the last question, I think this is a really clever little question. What is the actual number of commercial aircraft flying in 1992? Notice you don't have a plot, the original scatter plot. You don't have the original X and Y explanatory and response values plotted anywhere. You only have a plot of the residuals. But you do know what a residual is. A residual is the difference between the actual value of y and the predicted value of y. So notice the actual value of y that we're trying to find minus the predicted value in 1992 should equal the residual from 1992. And I can read the residual for 1992 off of the residual plot. So 1992 is represented right here by an x value, an explanatory value of 2. That residual is positive 40. I can read that off of the residual plot. So now I can solve this really simple equation. The actual value minus the predicted value, notice that predicted value we found in part D, should equal the residual's value of 40. So again, showing this simple amount of work is really important when you're solving a question like this. So hopefully solving that shouldn't be particularly hard. The actual number of aircraft would have been 3,447. Knowing definitions then, for instance, the definition of a residual, actual minus predicted value, that's the definition of the residual. Knowing how to interpret intercepts, knowing how to interpret slopes in context, knowing how to write a regression model so that you can use it to make a simple prediction. None of these ideas require a great deal of math, but they do require you knowing simple definitions and how to describe them in context. That's the most important skill in this unit. Hope this has been helpful.